Hello everyone, I'm Amrozia Shaheen from University of Argentina, and today I'm going to talk about the automated characterization of multi-view fringe projection system for 3D shape measurement of alien parts. So form measurement is critical in additive manufacturing because of complex free-form geometry and multiple occlusion and line of sight issues. So over the past decades, many methodologies have been developed for the dimensional characterization of AM parts, which can broadly be categorized as contact methods like CMM and non-contact, such as structure light techniques and photogrammetry, laser scanning, and X-ray computed tomography. So once the measurement is done, then comparison with the CAD model and the coarse measurement alignment provides a possible route to exploit all the a priori information. So a fringe projection is basically a non-contact optical method that has been extensively used in dimensional characterization of AM parts because of having non-contact, non-destructive, and fast acquisition nature and requiring millions of points in a second. And it has many applications in AM quality control, reverse engineering, biomedicine, and automotive and aerospace. So the basic idea is that we generate fringes or structure-like pattern in computer, which varies in intensity sinusoidally and have some phase difference. We project those fringes onto the surface of the object through a projector. These fringes get distorted after their projection, and the camera captures the distorted fringes from a different perspective. Usually, camera and projector are mounted in a triangular configuration. So since we encode information in terms of phase, we need to decode it, and there are specific protocols. Using those protocols and taking the phase difference, we get the height information through extensive image processing. So the base has a significant importance in fringe projection systems. So just to elaborate the concept of phase, there are three patterns that in which the intensity varies sinusoidally and that have a phase difference of 2π/3. So in digital signal processing, we determine phase in terms of tan inverse function, which has limits between -5 to π. So the phase always gets trapped between this limit. However, in order to reconstruct the signal, we need to apply a proper technique that is called phase unwrapping. That is to get the fringe order and by adding or subtracting a factor of 2π. So single camera projector based systems have this issue of getting the full form of AM parts in one acquisition because of small depth of field, multiple occlusions, shadows, and line of sight issues. Because structures like that have lattices, it's difficult to acquire the form because we cannot eliminate those areas with the structure type. Another constraint is the surface properties because AM surfaces are manufactured by layer processes and they are not optically smooth to visible pigments. And material range is another constraint because different materials have different reflection and absorption coefficients, so which inhibits an overlay of specific pigments. In the industrial sectors, commercially available fringe projector systems are not cost effective. And in these systems, the object needs to be rotated multiple times or the system itself is mounted on a robotic arm in order to acquire the full form of AM objects. So in order to address these issues, we at the manufacturing metrology team at the University of Argentina working to develop a multi-view fringe projection system. And my professor called it Jabe, which is a Persian word that means a ball. So on the left-hand side, you could see it's Jabe. It has right now 8 cameras, like 2 cameras in each quadrant. And we need to decide how many projectors we can add in order to illuminate the object. So this is the status of the setup that we currently have in the manufacturing metrology team. It comprises of 4 sets of cameras and projectors, and these cameras and projectors are mounted on rigid frames. So this system is less prone to vibration that arises, vibration that comes in because of seismic and acoustic noise. So normality of multi-view consideration system is that since we're going to use since we capture information from different perspective, so we are aiming to make a robust system and high-speed system. With this system, we will get full 3D coverage or high dense point cloud because it will be a combination of different point clouds. And then the calibration errors can be improvised by improvising the calibrations of the cameras and projectors that we are using in this setup. So characterization is the first and foremost important step in the fringe projection technique. It's basically to characterize all the cameras and projectors. But when it comes to a multi-view system, then it's a challenge because all the cameras and projectors need to be in a global frame of reference. A camera is basically modeled as a pinhole model, which is basically on the left-hand side, you can see a projection of a point that is denoted as P with coordinates X, Y, Z onto the camera frame. So it's basically the correspondence between the world coordinates and the image coordinate, and it's usually denoted by this equation where R and T are the rotation and translation of the point or from the world coordinate to the image sensor or image coordinate, and UV are the coordinates in the image domain. But when it comes to projector, then it's difficult. We need some extra information in order to characterize the projector, and we encode that information in terms of phase. Imagine we are projecting horizontal phase shifted pattern. It corresponds to in the phase map that is noted by as 5V. It corresponds to one line, which is related to a line in the camera image. And this line corresponds to many points in the projector image. However, if this line is intersected with an orthogonal line, which is done by projecting vertical fringes, then it corresponds to a specific point, and it leads to one-to-one correspondence between the camera image and the projector image. So here is the pipeline that we follow to characterize our multi-view fringe projection system. That we have a calibration architect, checkerboard. We take images of the checkerboard and determine the camera parameters. In order to characterizing projector, we project horizontal and vertical fringes onto the checkerboard. And we are combining sinusoidal and binary fringes in order to get absolute phase information. And from there, we get the projector parameters. Once we got camera and projector parameters, then all the cameras and projectors are in the global frame of reference, and then we can use this characterization in order to perform a measurement, for which we take each camera and projector as a stereo pair, and using the principle of triangulation, we determine the 3D shape of AM parts, and further we use the ICP algorithm in finite registration. So just to start up as a multi-view system, we used 2 sets of cameras and projectors. So here are the results for camera characterization, which are basically the extrinsic parameters and the reprojection error that are used to evaluate the accuracy of the calibration. So on the left-hand side, you could see the extrinsic parameter visualization correspond to the orientation and location of the camera. And the colorful images they correspond to the checkerboard position. So from these results, you could see that all the positions are within the measurement volume. On the left-hand side is the reprojection error. It's basically the error between the point detected on the checkerboard point and the projection of that point from the world coordinate to the image coordinate. And these from these graphs, you could see that the error is less than half a pixel. and using the horizontal and vertical fringes and the pipeline that I showed you before, we characterize projectors as well, and the external parameters correspond to the orientation and location, and you could see that there is no anomaly, and the reprojection errors are a bit higher than camera parameters, but they are still less than around half a pixel. Okay, once the characterization is done, then the measurement process comes in. Since we are using two projectors and cameras, so for two different perspective two cameras sees different information, and by which we got these 4 point clouds. Here is the result, that is the consolidated form of all the point clouds, and the final one you could see the dense point cloud. Okay, this is the point cloud that we have got using one camera and projector. Since we are projecting only from one side and the camera captures from that side, so there are voids or missing information on 3 sides. With 2 sets of cameras and projector, we could get information on the 2 sides, and by introducing more cameras and projector, we are able to get complete information of the artifact that we measured. Okay, and coming to the conclusion, so we are using the fringe selection technique that has many advantages and extensively used in the 3D shape measurement, but still there are some challenges associated to single cameras and projector, like small field of view collisions and high slope angles. To address those issues, we are working on a multi-view fringe projection system, and it has the advantages of capturing the specular and diffuse reflection. And we characterize that system by determining the intrinsic and extrinsic parameters of all the cameras and projectors, and in a global frame of reference. And after the characterization, we determine the 3D shape of an EM part that was the nylon 12. So the future will include that we are working on a method in which we don't need to calibrate or characterize the projector. Also, we're working on the optimization that is associated with pulse estimation and the speed of the system. And in the point clouds that I've shown you before, you could see that there are some noise that is associated to the phase measurement errors. We are trying to address those issues as well. And also, we are going to incorporate all the API information by including the computer design and the system of that. Thank you very much for your attention.
Thank you, Amrozia. Are there any questions?
After the calibration method, do you also do some kind of fitting, or is it just basically you use the calibration?
I use the ICP, iterated closest point algorithm, taking as a first point as a reference, and then the other point clouds. Since we still have some noise issue and we need to optimize it using the bundle adjustment approach, so after that we will go to generate the heat map and align with the CAP model.
When you use multiple projectors, did you eliminate the components sequentially, spatial order?
In order to address the cross-talking between projectors, we trigger one projector at a time. So one projector projects and all cameras capture, and then we move to the second one.
Do you think it could be done by using different colors?
Yeah, it's possible. Yeah, that will add speed to it, but these are just preliminary results, so yes.
So these are all the questions. I suggest we thank Amrozia again.